NENOMATICA, where mathematics meets YouTube excellence. Welcome to this mathematical proof video. Today, we'll solve an algebraic problem that requires substitution and factoring techniques. Let's start with our problem. We need to show that if it equals b, then the following expression equals 0. A squared times b squared times the quantity b minus a plus b squared times c squared times the quantity c minus b plus c squared times a squared times the quantity a minus c. This is a classic example of algebraic substitution and manipulation. We'll need to carefully substitute the condition at equals b into the expression and see if we can prove it equals 0. Let's approach this step by step. First, we'll focus on the first term of our expression. We'll use the substitution rule, where we replace every occurrence of b with a, since we're given that a equals b. The first term is a squared times b squared times the quantity b minus a. When we substitute b equals it into this term, we get a squared times the quantity a minus a. This simplifies to a to the power of 4 times 0, which equals 0. So our first term vanishes completely. Now, let's move on to the second and third terms. We'll continue applying our substitution rule, replacing b with a. The second term is b squared times c squared times the quantity c minus b. When we substitute b equals a, this becomes a squared times the quantity c minus a. Similarly, the third term is c squared times the quantity a minus c. Since b equals a, this term remains unchanged as c squared times the quantity a minus c. Now, we can combine the remaining terms. We'll use the factoring rule to extract common factors. Let's put the two non-zero terms together. A squared times the quantity c minus a plus c squared times the quantity a minus c. Notice that both terms have a common factor of a squared times c squared. So we can factor this out to get a squared times the quantity c minus a plus a minus c. Inside the brackets, we have c minus a plus a minus c, which simplifies to 0. Therefore, the entire expression equals a squared times 0, which is 0. Let's now verify our complete solution. Our original expression was a squared times the quantity b minus a plus b squared times the quantity c minus b plus c squared times the quantity a minus c. With the condition that it equals b, we found the first term equals 0. The second and third terms, when combined, also equal 0. Therefore, the entire sum equals 0, which proves the statement. Let's recap the key techniques we used in this proof. First, we applied direct substitution by replacing b with a. Second, we recognized that the first term vanished completely. Third, we factored out common terms from the remaining expressions. Finally, we identified that the terms inside the bracket summed to 0. This problem demonstrates the importance of understanding substitution in algebraic expressions. We have three expressions, a, b, and c. A equals negative m times the quantity 2x minus 1, all multiplied by y. B equals 4y times the quantity 1 minus x, all multiplied by m. C equals mx minus 1/2. And we need to simplify the expression 2a minus the quantity 1/2 b minus 2c. Let's tackle this step by step. First, we'll calculate 2a. We use the definition of a and multiply it by 2. 2a equals 2 times negative m times the quantity 2x minus 1 times y. We can distribute the 2 to get negative 2m times y times the quantity 2x minus 1. Then we expand the expression further to get negative 4mx y plus 2my. Next, let's calculate 1/2 b. Similar to the previous step, we use the definition of b and multiply by 1/2. 1/2 b equals 1/2 times 4y times the quantity 1 minus x times m. Simplifying the coefficient, we get 2my times the quantity 1 minus x. Expanding this, we get 2my minus 2mxy. Now, we'll find 1/2 b minus 2c. We need to calculate 2c first, and then subtract it from 1/2 b. 2c equals 2 times mx minus 1/2. Distributing, we get 2mx minus 1. Now we can form 1/2 b minus 2c. We take our expression for 1/2 b, which is 2my minus 2mxy, and subtract 2mx minus 1. which gives us 2m y minus 2m x y minus 2m x plus 1. Finally, we can calculate the entire expression, 2a minus the quantity 1/2 b minus 2c. We substitute the expressions we've already calculated. 2a minus the quantity 1/2 b minus 2c equals negative 4 m x y plus 2m y minus the quantity 2m y minus 2m x y minus 2m x plus 1. Distributing the negative sign, we get negative 4 m x y plus 2m y minus 2m y plus 2m x y plus 2m x minus 1. Now we can combine like terms. Combining the mxy terms, we get negative 4 mxy plus 2mxy, which equals negative 2mxy. The my terms are 2my minus 2my, which equals 0. So our final simplified expression is negative 2mxy plus 2mx minus 1. Let's look at our example. We are given three expressions. A equals 1 minus 2x squared, b equals 3x squared minus 4x plus 1, and c equals x squared minus x. Our task is to compute the expression a plus b minus 3c. Let's approach this step by step. First, we'll calculate a plus b. We substitute the expressions. A equals 1 minus 2x squared, and b equals 3x squared minus 4x plus 1. When we expand the parentheses, we get 1 minus 2x squared plus 3x squared minus 4x plus 1. Now, we combine like terms. Negative 2x squared plus 3x squared gives us x squared. 1 plus 1 gives us 2. So a plus b equals x squared minus 4x plus 2. Step 2, let's calculate 3c. We substitute c equals x squared minus x. Distributing the 3, we get 3 times x squared minus 3 times x, which equals 3x squared minus 3x. Step 3, now we need to subtract 3c from a plus b. We substitute our previous results. A plus b equals x squared minus 4x plus 2, and 3c equals 3x squared minus 3x. Subtracting means we change the signs in the second expression. So we get x squared minus 4x plus 2 minus 3x squared plus 3x. Step 4. Finally, we combine the like terms in our expression. Let's look at the x squared terms. X squared minus 3x squared equals negative 2x squared. For the x terms, negative 4x plus 3x equals negative x. And we have plus 2, so our final answer is negative 2x squared minus x plus 2. Let's start with our problem. We have a rectangle with length 3 units and width 2 units. Then, we increase both the length and width by x units. We want to find out what the new area will be. To find the area of the rectangle after the increase, we need to multiply the new length by the new width. The new length is 3 plus x, and the new width is 2 plus x. So the area is given by the product of these two expressions. Now, let's expand this product using the distributive property. We'll first multiply 3 plus x by 2, and then multiply 3 plus x by x, and add these results. Now, let's expand these products further. X times x plus 2 gives us x squared plus 2x, and 3 times x plus 2 gives us 3x plus 6. Next, we combine like terms. We can add 2x and 3x to get 5x. So our expression becomes x squared plus 5x plus 6. Let's verify this result by thinking about the area geometrically. When we have a rectangle with length 3 plus x and width 2 plus x, we can divide it into 4 parts. A rectangle with area 3 times 2, or 6. A rectangle with area 3 times x. A rectangle with area x times 2. And a square with area x times x, or x squared. When we add these areas, we get x squared plus 3x plus 2x plus 6, which simplifies to x squared plus 5x plus 6. In this video, we'll derive the formula for the area of a trapezoid by using the areas of triangles. Let's start by examining the figure shown. We have a trapezoid composed of 2 triangles, a red triangle and a blue triangle. The trapezoid has 2 parallel sides, one with length r at the top and another with length b at the bottom. Both triangles have the same height h. First, let's calculate the area of the red triangle. We know that the area of a triangle is 1/2 times the base times the height. For the red triangle, the base is b and the height is h. So, the area of the red triangle is s equals 1/2 times b times h, which equals 1/2 bh. Next, let's calculate the area of the blue triangle. Similarly, we use the formula for the area of a triangle. For the blue triangle, The base is a and the height is h. So the area of the blue triangle is S2 equals 1/2 times a times h, which equals 1/2 AH. Now, let's find the total area of the trapezoid by adding the areas of the two triangles. The area of the trapezoid, S equals S plus S2. Substituting the values we found for S and S2, we get S equals 1/2 BH plus 1/2 AH. We can factor out the common term 1/2 H to get S equals 1/2 H times B plus A. Rearranging the terms, we can also write this as S equals 1/2 times A plus B times H. Welcome to our math video. Today, we'll derive the formula for the area of a trapezoid by breaking it down into simpler shapes. Let's consider a trapezoid. We have a trapezoid with parallel sides. The top side has length A, and the bottom side has length B. The height of the trapezoid is h. We can divide this trapezoid into three parts. A blue triangle on the left side with base y, a white rectangle in the middle with width a, and a pink triangle on the right side with base x. Let's calculate the area of each part, and then sum them up. For the blue triangle on the left, the area S1 is 1/2 times base times height, which is 1/2 times y times h. For the white rectangle in the middle, the area S2 is simply the width times height, which is a times h. For the pink triangle on the right, the area S3 is 1/2 times base times height, which is 1/2 times x times h. Now, the total area of the trapezoid, S, is the sum of these three areas. S equals S1 plus S2 plus S3. Substituting our expressions, we get S equals 1/2 YH plus AH plus 1/2 XH. We can factor out h to get S equals 1/2 YH plus 1/2 XH plus AH, which can be rewritten as S equals 1/2 H times the quantity Y plus X plus 2A. We know that the bottom base B equals Y plus A plus X. Therefore, Y plus X equals B minus A. Substituting this into our area formula, S equals 1/2 H times the quantity B minus A plus 2A, which simplifies to 1/2 H times the quantity B plus A. Therefore, the area of a trapezoid is. Welcome to our math problem-solving video. Today, we'll find the ratio of areas between a golden rectangle and the original rectangle. Here's our problem. The ratio of length to width of a rectangle is 5:4. By increasing the length of the rectangle, we'll get a golden rectangle. What is the ratio of the golden rectangle's area to the original rectangle's area? Let's start by defining the dimensions of our original rectangle. Since the ratio of length to width is 5:4, we can represent the length as 5x and the width as 4x, where x is some unit of measurement. The area of this original rectangle is the product of its length and width, which is 5x times 4x, giving us 20x squared. Now, let's understand what a golden rectangle is. A golden rectangle has the special property that the ratio of its length to width equals the golden ratio, phi, which is approximately 1.618, or exactly 1 plus the square root of 5, divided by 2. To transform our original rectangle into a golden rectangle, we need to increase its length by some value y. So the new length becomes 5x plus y, while the width remains 4x. Since this new rectangle must be a golden rectangle, the ratio of its length to width must equal phi. That means 5x plus y divided by 4x equals phi. Now, let's solve this equation for y. First, we multiply both sides by 4x. We get 5x plus y equals 4x times phi, which is 4x times 1 plus square root of 5, divided by 2. Simplifying the right side, we get 2x times 1 plus square root of 5. Now we can solve for y by subtracting 5x from both sides. This gives us y equals 2x times 1 plus square root of 5 minus 5x. Distributing and simplifying, we get y equals 2x plus 2x square root of 5 minus 5x, which equals x times 2 square root of 5 minus 3. Now we can calculate the area of the golden rectangle. The area is the product of its length and width, which is 5x plus y times 4x. Substituting our expression for y, we get 5x plus x times 2 square root of 5 minus 3 times 4x. This simplifies to x times 5 plus 2 square root of 5 minus 3, which equals x times 2 plus 2 square root of 5, multiplied by 4x. So the area of the golden rectangle is 4x squared times 2 plus 2 square root of 5. Now, we can find the ratio of the golden rectangle's area to the original rectangle's area. The ratio equals S sub gold divided by S sub first. Substituting our expressions for the areas, we get 8x squared times 1 plus square root of 5 divided by 20x squared. We can simplify this by canceling out the x squared terms, and we get 8 divided by 20 times 1 plus square root of 5. This simplifies to 2/5 times 1 plus square root of 5. Let's calculate the approximate numerical value of this ratio. Since the golden ratio phi equals approximately 1.618, our ratio equals 2/5 times phi plus 2/5. This gives us approximately 0.4 times 2.618, which equals about 1.047. So the golden rectangle's area is about 4.7% larger than the original rectangle's area. This fascinating relationship shows us yet another beautiful property of the golden ratio in geometry. Thank you for watching. Don't forget to like, subscribe, and hit the bell icon for more math lessons. NENOMATICA, where mathematics meets YouTube excellence.